Okay, so our next presenter is Martim Aguiar. He is invited professor of UVI and researcher at C-MAST. He holds a master degree in Electromechanical Engineering and is currently completing a PhD in Mechanical Engineering. He has contributed through different book chapters, papers in international journals, and today he will present his work on detection of frost formation in evaporators for control of demand defrosting operation. Many thanks.
Thank you. Good afternoon, everyone. So I will start presenting my work on the detection of frost formation in evaporators for control of demand defrost system. First of all, we need to talk about why we need refrigeration. We need refrigeration because especially perishable food products in the food industry, there are other applications in pharmaceuticals and so on. If stored under improper conditions, will have a reduced shelf life, which means that if we keep a lower temperature, we will increase the duration of quality in these products and eventually reduce food waste. With everything, there's a catch. We require a lot of energy to keep those refrigerant systems working. So what we have to do nowadays, if we do not want to increase the amount of food that we waste, is to increase the efficiency of those systems. So the first thing we can do is look at those systems, what can we improve in there, and what we work in here is the efficiency of heat exchangers, more specifically on the evaporator. One of the problems that affects this efficiency is the formation of frost on the surface of the heat exchanger. Frost forms a barrier on the thermal conductivity that decreases efficiency and can be affected by a lot of parameters such as air humidity, air temperature, the surface of the fins, and others such as air velocity and so on. There's a lot of parameters, so it's hard to compute based on the environmental conditions. This insulates the heat exchanger, and what we have to do is, when we have frost, we have to remove this frost in order to make the heat exchanger more efficient again. So what we do to solve this problem is implement defrosting operations. We have two types of defrost methods. We have restrained frost, which reduces the accumulation of frost, either by changing the characteristics of the inlet air. For instance, we can humidify the air and then we have less frost formation. We can change the cold surface characteristics and we can change the interactions. But frost will always form, and what we can do is then remove this frost. The most used method nowadays is still using an electric resistor with time defrosting delays. What happens is, as I told before, humidity changes across the day and across the seasons, as does temperature and does all the other parameters. So the requirements for defrosts vary according to the day, according to the seasons, according to the region of the world we are in. And for this, we have to do different defrosting periods. So if we do a defrosting every hour, for instance, we might require an increased amount of defrosting or a decreased amount of defrosting. If we have a blind system that does not operate based on the frost that is formed on the heat exchanger, we are losing a lot of efficiency. G et al. Did a study that he developed a sensor. It is a tap sensor that he applies on the tubing of the refrigerant and creates a relation between the frost formation on the refrigerant tubing and the evaporator itself. And in one of his studies, of course, this is for a specific temperature, for a specific application, for a specific system, he observed that it could reduce a lot of operations. Each dot in here represents a defrosting operation. This is a blind system that uses time defrosts, and this in here is a defrosting system that uses a sensor. So it is evident that we need to enhance the efficiency of the defrosting operations. What we have been developing is different methods of low-cost frost sensing. And to do this, what we came up with was a simple resistive sensor. It works based on the principle of different resistive on the mediums of two electrodes. we have an example here that has a sensor with two electrodes, and those electrodes measure a voltage drop. In this case, there's only air, so a specific resistance of the air. Air is insular, so it does not conduct. In here we have water, and this water absorbs some ions from the copper, and then it starts conducting. And here we have frost, and it's back to being insular. So we can detect if we have two electrodes. If you can, it's very important to have those electrodes at the same temperature as the surface of the heat exchanger, so it behaves just like the heat exchanger itself. We can detect the accumulation of water, and we can detect when this water freezes. So we can efficiently detect frost, water condensation, and frost deposition on the heat exchanger. There are several methods to enhance this detection, because if we use only two electrodes, vibrations, different droplet sizes, and so on, this is a very small sensor, you can keep that in mind, that can affect the efficiency of this sensor. So what he did was trying to use different methods. This one is a bare copper electrodes. Those two are an encapsulated sensor. This one uses the exterior as electrode. This one has an insulant external capsule. This one has a ceramic, a porous ceramic medium, and this has a fabric medium. We developed the sensor with test results. We tested all of them. Those are the bare electrode sensors, and these are the sensors with a fabric medium. The one with best results were those. Although fabric mediums are not good heat conductors, there's always some copper exposed that has that lower temperature and allows for water deposition. And besides that, because this medium absorbs water from the neighborhood, it absorbs water from the heat exchanger itself. And what we did to test these sensors was to apply them directly on the heat exchanger. We tried different positions, and we'll talk about that a little bit more in focus later. And we also added a camera facing the intake front of the heat exchanger. This heat exchanger has a refrigerant that, of course, is below freezing point of water. Water condensates, then it freezes, and frost and water are detected. That camera that faces the intake front is used to apply a computer vision method, because I can have a sensor in there, but to make sure that I am detecting frost, I have to have something besides me sitting near the sensor to confirm that it is actually working. So the camera takes a picture. You can see here where the sensor is placed. This one is a temperature and humidity sensor. It creates some noise on the readings. We'll also talk about that later. I will also talk about this later. This is fin damage, and we will look into it. We capture this image, and then what we do is binarize this image. Only white and black pixels. From this to this. What we do next is count the number of white pixels, count the number of black pixels, and then we create a relation that tells us the amount of frost on the sensor itself. So, for the testing, we apply this sensor on the heat exchanger, and this is what we measure. What we can see, first of all, we can see clear difference in measurements of the sensor and the camera in these points, like in here and in here, because the sensor has the ability to detect the presence of water, and the computer vision method also has that ability, but it is very slight ability to detect the position of water, because what is very contrasting is frost and the black background of the heat exchanger. So the water, it could be calibrated to detect it more efficiently, but what we really want to know is this part in here, how it compares between the camera, the computer vision method, and the sensor. We did some testing, some with better results than others. This was the sensor that yielded the best results. Also interesting in here, you can see how frost forms on the heat exchanger. It has an uneven frost formation. This can be caused by the airflow, by the refrigerant, how refrigerant flows inside the heat exchanger. Every evaporator is different in the frost formation pattern. But this gives us an average method. What we do is measure the frost across the whole heat exchanger and then average it and compare it to the sensor. but the sensor only detects frost in this small portion of the heat exchanger in here. So the next step is try to refine the frost detection using the computer vision method, and then enhance how we can evaluate different parts of the heat exchanger. What we did in here was divide the heat exchanger in 12 by 12 tiles. We named vertically in numbers and horizontally in letters, just like a chessboard. And then we binarize it and average the color to give us a frost formation map for every measurement we take. We then have a 3D matrix that is the variation of frost formation maps across time. Every measurement that we make with the resistive sensor corresponds to a frost formation map that we can then sum and get an average formation map of the frost across the testing that we did. In this case, it is very evident that we have here the sensor, so that is a noise. We can exclude this on our calculations, and we can see that we have very dark pixels and a lot more lighter pixels. This tells us that in those darker shades we have less frost formation, and those lighter shades we have a clearer frost formation. So we then analyze some tiles and we present some results in here. On this case, we see the computer vision method without tile refinement and the sensor. We can clearly see across all the 5 frost-defrost cycles that the camera detects according to the sensor. They are very well coordinated, although in different levels of detection. This is for detection of the whole frost across the heat exchanger, but then we refine and only analyze the tile, and what we check is that if we only analyze with the computer vision method, we can have a more accurate frost detection. We could, of course, offset this to calibrate it more accurately, but measuring the small tile where the sensor is placed tells us that the sensor is measuring frost a lot more accurately than we would say from those readings. Additionally, from this we could compare 2 different tiles that do not have problems, no sensor is placed in there, no defects observed visually on the heat exchanger, and we also check that in 2 different tiles you can have completely different frost formation patterns on the heat exchanger. And then we also try to analyze the impact of defects, and we specifically selected tiles with defects, tiles where the sensor is placed, and we see a very different frost measurement, and this will be later argued to be used as a diagnosis tool for the heat exchanger XR. The frost formation map helps us not only to see where we have more frost forming and less frost, and where we have sensors or defects, but it also helps us placing the sensor. If we want to use the placement of a simple low-cost sensor that uses a resistive 2 electrodes, this is a very low-cost sensor, instead of using a camera, we could use the camera to know where are we going to place the sensor. We will certainly not place it in here because this will be the last place where it will be detected. And maybe we don't want to place it in here either because this will be the place in which frost will be forming fast. We want an average knowledge of the frost formation on the heat exchanger. So according to how early of the detection we want, we can analyze the map and then choose where to place the sensor. In conclusion, this can be used, this image analysis method can be used to accurately know if the sensor is working very well or not. I showed you the best results. We also had sensors that do not work so well. And using the computer vision method, we can accurately know if the computer vision method is detecting frost. We know that there is in fact frost. If it does not detect, there is no frost. And we compare the plots, and then we know that there is in fact frost or not. And the best sensors can be selected this way. It can be also used to detect individually where the sensor is placed, and we can even add more sensors and detect how different tiles are measuring frost, and if those different placements of sensors are actually accurately measuring those differences in variation. And this can be a tool to understand how frost is being formed in our heat exchanger, which is very interesting if we want to study the efficiency of the heat exchanger in cooling the air evenly. If we have an uneven airflow, this map will tell us that the frost is not evenly being formed, and we have to analyze what are the problems, what are we doing wrong. If there are flaws in the heat exchanger, we can analyze it through the frost formation map. Instead of looking at hundreds of thousands of pictures, we can look at the map that compiles all of the frost formation captures and then take our conclusions, which makes this a tool for not only helping us detect the best sensor, but also detect flaws in the heat exchangers. So I conclude with this. I move over to answer questions. Thank you very much.